Here we have a folder, Logisim. This is our core itself, which embedded a video file. It uses data from this file. These files are written in such a format. So first is the version 20rev. It's just the program version, which is compulsory. Further, you can see data in blocks, 32 bits each, or by hexadecimal system, 4 bytes. This data is recorded into the file and read by the program. Now, how can we get these programs? To do this, we have another program. It's written in Python. Everything is clear here. We see 3 main cycles of hashing SHA-2056. And moreover, this program forms this data for us. Let's run a program and we'll see what is happening. For now, we'll close it. We need only work console. It asks us to insert hash of the previous block. These are ones of necessary data which are needed for Bitcoin hashing. Now let's have a look at where we can get it from. So-called blockchain explorers exist on the internet. I have 2 of them opened, 2 sites, so you can find absolutely any block and get any data out of it. Well, here I have a generate of random numbers, also taken from the internet, so nobody thinks it's a fake. Here I pointed the interval, for example, from 2000 to 3000. These are the numbers of the blocks. And now let's generate some random block. They give us a number 550, 817. Copy it and find the this block. It is found here. And it will also be found here. Alright. Let's check hash. It ends with 9E28. Here we also have 9E28. This is exactly this block. Now, just a second, I'll have a look at the time. Here it's 1.20, and here is 4.20. Alright, we'll need to work a bit more with time. Well, what are we doing? From this very data, we take what the program requests. Insert hash from the previous block. Here is hash of the previous block. We are highlighting it, copy, and paste. And now root Merkle is requested. Root Merkle is given in this line. We also copy it and paste. Now insert bit complexity or bits of the block. Here we have bits of the block. These are nonce. Nonce is a random number which we need to find while hashing, except hash. Now it requests the date of block hashing. The date is located here. The only thing we need to take into account is time shift. In this case, we need to plus 3. Now we'll check it, run hashing, and we'll see all the procedure in process. Here we see how it is hashing each new cycle. There are 64 cycles in each hash. One needs to pass 3 hashes. This means 3 hashes SHA-256 in order to get hash of the block, of any block. The second hash is finished and we are approaching the third one. We get the third hash and compare the correctness. So it must be correct. Let's check 289E. That's it, 289E. So we inserted the time correctly and we got the right hash. Now let's copy this data. In order to work more comfortably, let's copy all the data, or even let's do it a bit differently. Select all, copy, minimize the window, and here we have hash, highlight all, then paste. This data is unnecessary to save the file. Let's have a look for what we needed all this. I think you have already paid attention to the thing that when we get hash, it turns out to be maximized. Here we close it now because we don't need it. We'll use this text file. Let's have a look at our hash. It starts with 28, hexadecimal system. For those who know it, each two numbers in the hexadecimal system means byte. A byte which consists of 8 bits. However, in the hexadecimal system, we use not only numbers from 0 to 9, but also Latin letters. These are A, B, C, D, E, F. Therefore, we see those letters between numbers. You can see them. And when we count hexadecimal code, we need to take numbers by pairs. Here we see a pair 28. We see at the end of the block the next pair 9E, and we see that 9E is the one before the last, then 0, 0, and we see the following 0, 0, then 66 we have here at the beginning. So because of some reasons we got a maximized block. That's such a Bitcoin peculiarity. We have to decompress all these incoming data, modify time, modify nonce, modify bits. Because, for example, bits are now written in the decimal system and nonce are also written in the decimal system, and in order to hash it, one needs to make it in the hexadecimal format and decompress. That's what our program was doing. It gave us a full hash and it allowed us to write down data as well. Let's have a look. Here we completed to enter data and time. And here we have received data, the version of the block, hash of the previous block. Here it starts with zeros and ends with B9, the same root Merkle and bit complexity. Initially we got in the decimal format, now we have it in the hexadecimal one. Nonce of the block in the hexadecimal format, and from time in this format we get timestamp, also in the hexadecimal format, so-called Unix time. Now we need to decompress all these data. You see that if we take hash from the previous block, it ends with B9 and we have B9 at the beginning after decompressing. Next numbers 1D and we have it here at the beginning. Again B6, the second byte from the end, and the same with the root Merkle 84 and so on. So it ends with 92 and we have it in the end. The same thing with bit complexity, with nonce and timestamp. After this all, data must be joined consequently into one line. In this line after 9A, a special ending is added. Here it ends with 280. 280 is data size. This means number of bits in the incoming line. Totally this line is 256 bits, and now if we divide it into blocks into 4 bytes or 32 bits, we see the following. The block, the next one, in this very case we have a capitalized Latin letter A. You may not mention it, it simply determines a type of data, L, long, and it is sometimes added if data are over a specific number, but in fact this letter isn't in our calculations. Then our program gave us the first hashing, and besides this it created such a file for us, data.txt. It inserted all the data. Let's compare them again. We see this date 02, 6 zeros. Here is this block, B9 1D, B8 9E7. Here is this block, then B5 BE, and so on. Here is this block. In other words, all these dates are filled into this file. Now we can download this file directly into our simulation. Now let's run our hashing. Enter our program Logisim. We see our simulation. Now we need to download incoming data into our ROM. To do this, we need to download the image, which is recorded in the file data.txt. Open, download it. Let's check for a second. We see that data correspond completely. B91D, B91D, B8E7, B8E7, and so on. The last numbers here, 1C9A and 1C9A, 280 here and 280 here. It means that the data coincide. We can start hashing. To start hashing, we'll try it on the low clock speed, or let's make it a bit bigger so that the process of scanning goes faster. Turn on beats, but we'll need to stop it all in time. So let's run the procedure, and we see that the program is scanning data. Readiness number 0. Turn off automatic regime. Let's turn off automatic regime. A little is left to be scanned, and we'll do this manually, and then we run the program of hashing in order to see initial data. So we see initial data here, and we need to compare them. Let's open the file hash and look at hashing. Here it is, and let's compare. These are incoming start data. They are absolutely the same in all hashings, no need to show them. Now let's start to compare from the first round, to be concrete, the 0 round. Now we are ready to see what we get. The first calculations in manual mode. So the first cycle of hashing is made, and we compare FE08884D and FE08884D. The next one, 6A09E667, and here 6A09E667, and so on. You can check all the data coincide, as I've already said. The letter L is to be ignored, it just shows the long type. And we finish 1F83, 1F83, and D9AB. The next cycle, let's make some bits from which the calculation of the cycle derives. The calculation of the cycle is completed. Let's compare. Here we have round 1. To be concrete, it's number 2 in order, and we see the data absolutely coincides. At the end we have 8C, 8C. Let's make one more round. We did it. Let's look further. 69568574 and 69589574, and so on. This way there are 64 rounds, in fact 63, because numeration starts with 0. After it we get the first hash, and then the second hashing takes place. We start from round 64 and 64 more till 128. This will be the second hash, and at the end of the program will give us a resulting hash of the block. In order not to check it all in manual mode, I'll open a text document. We'll come back. I'll open some first rounds and show you them in manual mode. If you want, you can make a pause on the video and compare them. Well, now you will see the following round. This will be number 3. The next one, round 4, you can compare. The next, I'll show you some more rounds and then you compare yourself. Here it's 60 f2 and 60 f2 and so on. I'll show you all transient data slowly. If you want, you stop the video and compare. Now I'll run this simulation in automatic mode. It will count all the transient data so that you can be sure that our hashing works properly and it shows correct data at all stages. Certainly we need to wait for a while. However, there will be confidence that it's not a fake, but complete functioning architecture. It's all completed. Here is the end of the block. Now I will run the automatic procedure of modeling, first on 2 Hz, and then we'll see how it works. And turn on a bit faster. Let's take 4. With this speed, we'll have 1 hashing completely. The simulation is over. We can turn off the bits and I'll tell you further about other simulations. Now let's compare what we got. 289E0066, 289E0066, 8932, 8932, 70B5, 70B5, and so on. You see that hash is completely correct. It ends with 48 and then there are zeros. This way we got a completely correct hash. Thank you for your attention. Venus Mine Project. Good luck!